I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solutions of previous year questions from the section Analysis that have appeared in the CSIR National Eligibility Tests. In this video, we discuss 3 questions. Question number 18, 19 and 20. These questions are suitable for all these examinations. Right. This is the question from 2019 December question paper from part C for 4.75 marks. The question is related to mutually disjoint subsets of R. The given question is, which of the following statements are true? We are given 4 options. Option 1, there exist 3 mutually disjoint subsets of R, each of which is countable and dense in R. Option 2, for each n belongs to the set of natural numbers, there exists n mutually disjoint subsets of R, each of which is countable and dense in R. Option 3, there exists countably infinite number of mutually disjoint subsets of R, each of which is countable and dense in R. Option 4, there exists uncountable number of mutually disjoint subsets of R, each of which is countable and dense in R. Question looks to be very tough. Right. We will now discuss the solution of the problem in detail. Define a relation tilde on the set of real numbers by, for all xy belongs to R, x related to y, x tilde y, if and only if x minus y belongs to Q, the set of rational numbers. It is easy to see that this relation tilde is an equivalence relation on R. That is, this relation tilde is reflexive, symmetric and transitive. Now we define equivalence classes under this equivalence relation tilde. The equivalence class of x is denoted by bracket x, that is the equivalence class of x. It is defined as the set of all those y belongs to R such that y is related to x by tilde. That is equal to the set of all those y belongs to R such that y minus x is a rational number belongs to Q. That is this is the set of all those y belongs to R such that y belongs to x plus Q. That is, it is precisely x plus Q. Right. It's like cosets. Right. Now, clearly, each equivalence class is countable because Q is countable and dense because Q is dense in R. It is known that any 2 equivalence classes are either equal or disjoint. If x belongs to Q, then equivalence class of x is x plus Q is Q because x belongs to Q. For any I belongs to R minus Q, for any I in a rational number, then the equivalence class of I, that is bracket I, is I plus Q. Agreed. Now let S be the set of all equivalence classes of R. Now, how many equivalence classes will be there? As many as there are the irrational numbers. How many irrational numbers are there? Uncountably many. Therefore, S is uncountable. Why? Because the set of irrational numbers is uncountable. Now, let's look at our options. And we have argued that S is uncountable. So, the option 4 is true. Thus, option 4 is true. And when you have an uncountable number of them, you can extract 3 of them. You can extract finitely many of them. You can extract countably infinite number of them from S. So, the options 1, 2, 3 are also true. Why? Because we can extract finitely many, that is 3 or finitely many, and countably many elements from S which have the given properties. What are the given properties? What are the given properties? It must be disjoint, mutually disjoint dense subsets. Yes. Right. So the answer to this question, all options, option 1, 2, 3 and 4 are true. That is the detailed discussion of the solution of the given problem. And it is definitely a tough question in the examination hall. After you come out and look at the answer, most probably you say that it is very easy. Agreed. We move on to the next question. This question is from 2017 December question paper for 3 marks. It is related to one-to-one and onto functions. Let Z denote the set of integers and Z greater than or equal to 0 denote the set of non-negative integers, that is the set consisting of 0, 1, 2, 3, etc. Consider the map F from Z greater than or equal to 100 cross Z to Z defined by f of m comma n is equal to 2 power m multiplied by 2n plus 1. Then the map F is, we are given 4 options. Option 1, onto but not 1, 1. Option 2, 1, 1 but not onto. Option 3, both 1, 1 and onto. Option 4, neither 1, 1 nor onto. Let's now discuss the solution of the problem in detail. We have Z, the set of integers. Z greater than or equal to is the set of non-negative integers. We are given the map F from the Cartesian product Z greater than or equal to 0 cross Z to Z defined by f of the ordered pair m comma n is 2 power m multiplied by 2n plus 1. Now, we are trying for the one-oneness, that is it injective. For that, f of m comma n is equal to f of p comma q. By definition, 2 power m multiplied by 2n plus 1 is equal to 2 power p multiplied by 2q plus 1. Now, equating the even ones and the odd ones, we get 2 power m is equal to 2 power p and 2n plus 1 is equal to 2q plus 1. 2 power m is equal to 2 power p will imply m is equal to p. And 2n plus 1 is equal to 2q plus 1 will imply n is equal to q. Thus, the ordered pair m comma n is equal to the ordered pair p comma q. Thus, this says it is 1 to 1. F is 1 to 1. That is injective. Now, let us test for ontoness. Note that 2 power m is not 0. Agreed. For any m belongs to z greater than or equal to 0. And 2n plus 1 is also not equal to 0 for any n belongs to z. Yes. Yes. So, this will imply f of m comma n is equal to 2 power m, which is not equal to 0, multiplied by 2n plus 1, which is not equal to 0, the product not equal to 0 for any ordered pair m comma n coming from the Cartesian product z greater than or equal to 0 cross z. This implies there does not exist an ordered pair m comma n belongs to the Cartesian product such that f of m comma n is equal to 0. That means to say that the 0 that is there in the codomain, the codomain is z, has no preimage as no ordered pair m comma n in the domain such that f of m comma n is equal to 0. So, this implies 0 belongs to z, has no preimage in z greater than or equal to 0 cross z. That is, f is not onto. Thus, f is 1, 1 but not onto. Look at the options above. So, option 2 says it's 1, 1 but not onto. Therefore, the answer to this question is option 2. And the options 1, 3, 4 are not true. The answer to this question is option 2. That is the detailed discussion of the solution of the given problem, which is very, very easy question. Move to the third question and the last question in this video. Right, that is a question from 2017 December for 3 marks, that is from part B. It is related to countable and uncountable sets. The given question is, which of the following is necessarily true for a function f from x to y? We are given 4 options. Option 1, if f is injective, then there exists a function g from y to x such that f of g of y is equal to y for all y belongs to y. Option 2, if f is surjective, then there exists a function g from y to x such that f of g of y is equal to y for all y belongs to y. Option 3, if f is injective and capital Y is countable, then x is finite. Option 4, if f is surjective and x is uncountable, then y is countably infinite. Right. Let's now discuss the solution of the problem in detail. We have a function f from x to y. We take the option 1, that is, if f is injective, then there exists a g from y to x such that f of g of y is equal to y for all y belongs to y. We are given f is 1, 1, that is injective. Now, for g, a function from y to x to exist such that f of g of y is equal to y for all y belongs to y. What is the meaning of this? That is, f compose g is an identity map on y. Right. Now, let's recall a result. on functions. If f is a map from A to B and G is a map from B to A such that G compose F is IA, the identity map on A, then F is 1, 1 and G is onto. You remember, G compose F is IA, F is 1, 1, G is onto. So in our question, F compose G is IY means what? G is 1, 1 and F is onto. From this, G is 1, 1 and F is onto. But our function F is given to be 1, 1 and the ontoness is not given. Therefore, there does not exist a G satisfying this one. So it is not necessary. So since F is given only 1, 1, option 1 is not necessarily true. Right. We move to the next slide for the discussion of the remaining options. Option 2. If F is surjective, then there exists a map G from Y to X such that F of G of Y is equal to Y for all Y belongs to Y. Given F from X to Y is surjective, as onto, that means to say every element Y belongs to Y in the codomain has a pre-image X belongs to X such that F of X is equal to Y. Right. Now define a function G from Y to X by choosing each Y belongs to Y one of its pre-images in X. This is possible because F is surjective. Right. This G, what you have taken from Y to X, choosing for each Y belongs to Y, one of its pre-images in X, satisfies F of G of Y is equal to Y for all Y belongs to Y. You can check. Thus, the option 2 is true. Move to the next option, option 3. If F is injective and Y is countable, then X is finite. Is it so? Given F, X to Y is injective and Y is countable. When F is X to Y and it is injective, we have the inequality about the cardinalities of these sets. Because it is injective, this will imply the cardinality of the domain is less than or equal to cardinality of the codomain and Y is countable. That means cardinality of X is less than cardinality of Y and Y is countable. Therefore, X is also countable. That means X is either finite or X is countably infinite. Two possibilities are there. But in the option 3, only one possibility is given. Therefore, it is not necessarily true. The other possibility is also there. Therefore, option 3 is not true. Let's move to the fourth option, the last option. If F is surjective, X is uncountable, then Y is countably infinite. Given F X to Y is surjective and X is uncountable, when it is surjective, the cardinality of Y is less than or equal to cardinality of X and X is given to be countable. So, cardinality of Y less than or equal to cardinality of X and X is uncountable. Therefore, Y is also y is uncountable. Cardinality of y less than or equal to cardinality of x is uncountable, then what can be y? Y is either finite. If it is finite, cardinality of y is less than or equal to cardinality of x is uncountable. Or y is countably infinite, that is its cardinality is LF naught and cardinality of x is c, LF naught is less than c, that's also possible, and y is uncountable. So we have three possibilities. But in the option 4, it is given only one possibility, and the other two can also happen. Therefore, it is not necessarily true. Therefore, option 4 is not true. Thus, the answer to this question is option 2. That is the detailed discussion of the solution of this problem. And except for the first question, the remaining two questions are very, very easy questions. I am sure that you have understood the solutions of all these three questions. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Let's hope to meet you once again in another episode of learning. Keep learning. I wish you all the best. Thank you.